Welcome to part 2 of our discussion on probability distribution, essentially univariate probability distributions. In our previous class, we've been looking at introduction to probability, and then we also saw the properties of probability distributions. So today we are going to be examining mathematical expectations and moments of random variables and how they apply to probability distributions. Okay, now mathematical expectations, or the expected value of a random variable, it could also be the mathematical expectation or the expected value of a function of a random variable, is actually a long-run average value of that random variable when we repeat an experiment many times. So it is actually a quantity that captures the long-run average value of a random variable, say a random variable x, when an experiment is repeated several times. So it is denoted as expectation of x, which is E of x. So when we say E of x, we are trying to compute the expected value of x, which is the long-run average of x under the condition of repeated experiment. So the expected value is actually computed differently for discrete and continuous random variable. Recall in our previous discussion, we saw what discrete random variables are and what continuous random variables are. So discrete random variables being variables that random variables that assume values, specific values, or countable values. It's quite different from continuous random variables, which are random variables that assume value in some interval. So whenever we are computing the mathematical expectation of a random variable, it is usually important for us to first know the type of random variable whose mathematical expectation or whose expected value we are trying to compute. Okay, so computing the mathematical expectation for discrete random variables and for continuous random variables we follow different procedure. So we're going to see how we proceed under those two situations. So if x is a discrete random variable, the expected value of x is actually computed using this relation. Expectation of x is we sum the value assumed by the random variable, and then after they are multiplied by the probability mass function. Now, if we check this relation here, we'll see that f of x here, if x is a discrete random variable, f of x here is the probability mass function. Recall, the probability mass function is used to compute the probability that the value, is used to compute the probability of the values assumed by the random variable. Or if x is a random variable that assumes a value 2, the probability mass function is used to compute the probability that x is equals to 2. So when we are trying to compute the expected value of x, we use the value, this lowercase x, which the capital X assumes, to multiply the probability that x, this random variable x, assume this value x. So you see, computing mathematical expectation is sort of like summing all the values assumed by the random variable x after they have been multiplied by a weight. That weight is the probability that the random variable x is equal to that specific value. So you see, it's a weighted version. It's like we are weighting the sum of all observations that this random variable x assumes. So f of x here is the probability mass function of x, and x, this lowercase x, is the value that is assumed by the random variable x, and the sum is taking over all possible values that x assumes. So by now, we should be used to this nomenclature of taking the uppercase letter as the random variable itself and the lowercase letter as the value assumed by the random variable. So, for example, if this random variable x assumes some finite set of countable values, say they assume a value x1, x2, x3. Of course, x1, x2 down to xn are all integers. They are values, they are countable values. So, if we assume that they are finite, in other words, x1 down to xn, we have a finite set of values that this random variable x assumes. The expected value of this random variable x, given all these values that the random variable x assumes, is computed using this formula. And here, this is an expanded form. This here is an expanded form of this relation here. So the expected value is actually when we use each of the values assumed by x to multiply their probabilities, okay? Now, this probability is computed, this f of x1, for example, is computed from the probability mass function. So f is the probability mass function of this random variable x. So, for example, if x is a binomial random variable, f here will be the binomial probability mass function. So what we do is we use each of these observations that this random variable x assumes to multiply their respective probability and sum everything together. When we sum everything together, we get what is called the expected value of the random variable x. So for a discrete random variable, this is how we proceed with the computation of the mathematical expectation or the expected value of a random variable. Now, let us see the case where x is continuous. Now, if x is continuous, we know that x would be assuming a value in an interval, and that interval, of course, will be on the real line. Okay, so the expected value of x is also the product of the value assumed by x and its probability density function. So you see, for the discrete case, the random variable x, what is consistent with the random variable x is the probability mass function. But in the continuous case, what is consistent with the random variable x is the probability density function. So what we do is, since x is continuous, we can no longer use a sum as we did with the discrete case. We can no longer use a sum as we did with the discrete case. Now, since x is continuous, we are not going to use an integral. So we're going to integrate the product of this function, x and f of x, over the entire range of the random variable. Of course, that range is on the real line. That range, or the interval, is on the real line. So the expected value of a continuous random variable is the integral of the product of the value assumed by the random variable in a certain interval and the probability density function. Okay, so f of x here is essentially the probability density function, or the PDF of the random variable x, and x is the value assumed by x, and the integral is taking over the entire support or the entire range that x allows, okay, or that x assumes. So this is how to proceed with the computation of the mathematical expectation of a continuous random variable. So just for the case of an example, suppose x assume values in this open interval, okay, a and b. Of course, a can be any number. A can be negative infinity and b can be infinity, or a can be 0 and b can be infinity. A can also be 1, A can also be 0, and B can be 1. Okay, it can be any interval. However, the interval will be defined on the real line. Now, if X assume values in this interval, of course, it means X assume uncountable set of values in that interval. Now, the expected value of X being a continuous random variable, is given by this relation. Now, this relation here is an expanded form of this in the sense that, you see, the interval runs from A to B. So we're going to be integrating this function here with respect to X from A to B. Now, this gives us the mathematical expectation of a continuous random variable. Now, just for the record, we have just practically explained how to proceed with the computation of mathematical expectation of a random variable. Sometimes the interest might also be the computation of the mathematical expectation of a function of this random variable X. And the formula does not really change. The only thing that changes is just the function itself. Of course, the function of this random variable X will be replacing this, this quantity X here. So this is how to proceed with computation of the mathematical expectation of a continuous random variable. Now, for mathematical expectations of random variables, there are some properties that are very important for us to note, okay, when we are computing the mathematical expectations of random variables. There are some properties that are so important. Now, the first is if C is a constant, okay, C being a constant means C is not a random variable. The mathematical expectation of C is equal to C. In other words, the expectation of a constant will always be a constant. Now, the reason it's a constant is that C, being a constant, is not random, okay? It only assumes one particular value. So, on average, what we have to expect when that value occurs, that fixed value occurs all the time, would always be that same value. So, the mathematical expectation of a constant will always give you a constant. The mathematical expectation of 2 will be equal to 2. The mathematical expectation of 10 will always be equal to 10. Okay, now another property of mathematical expectation of random variables is if X is a random variable and A and B are some constant, okay, they are not variables. A and B are not variables now, they are constant. Then the expectation of the product of A and the random variable X plus B is equal to the product of A and the expectation of X plus B. Now, this property is called the linearity property of expectation, the linearity property of expectation. So what we do is, you see, the expectation will affect the variable. Of course, the constant is at the back of the variable. We have to take the constant here. So essentially, if we take the expectation of A here, it's going to give you A. If you take the expectation of X here, it's going to give you expectation of X. This is a positive sign, okay? Plus the expectation of B. The expectation of B will always give us a B because B is a constant. Okay, so this property is very useful in probability theory. Okay, and it's called the linearity property. Now, another property of mathematical expectation of random variable is that if x1 and x2 are two random variables, then the expectation of the sum of x1 and x2 is equal to the sum of their respective expectation. So this rule is telling us that the expectation of the sum of two random variables is the sum of their expectation. Now, we can also extend this property for n random variables. So if we have n number of random variables, say 10 random variables, the expectation of their sum is equal to the sum of their expectation. So this holds for random variable. Now, following that same pattern, if x1 and x2 are two random variables, the expectation of their product is also the product of their expectation. So if I have two random variables, x1, x2, and I'm trying to compute their expectation or to take their expectation, the expectation of their, the expectation of their sum, okay, the expectation of their sum is equal to the sum of their, the expectation of their product is equal to the product of their expectation. So basically, that is how we proceed when dealing with a random variable. These are the properties of mathematical expectations of random variable. Okay, now let's quickly discuss moment of random variable, because moment of random variable actually takes strength from mathematical expectation. So the moment of a random variable about a point, because when we talk about the moment of a random variable, we always address that moment to a particular point, okay? And this moment of a random variable is a measure that helps us to capture the shape and spread of probability distribution relative to a particular point. Okay, so by definition, the arrowed moment of a random variable x about a point A is given by this relation. Okay, now this arrow is a positive integer. For example, if we talk about the first moment, arrow becomes 1. If we talk about the second moment, arrow becomes 2. If we talk about the third moment, arrow becomes 3. So here, what we're saying is that the arrowed moment of a random variable about a certain point A is the expectation of the arrowed power of that random variable when the random variable is shifted by some constant. This shift constant here is the point at which we are taking the moment. Okay, that is the point at which we're taking the moment. Now, so again, the arrowed moment of a random variable x about a certain point A is the expectation of the arrowed power of that random variable when the random variable is shifted by the constant A, where this constant A is the point about which we are taking the expectation. So here, if A is equal to 0, we have what is called the raw moment, or the moment of the random variable about 0. Okay, if A is equal to 0, we have the raw moment, or the moment of that random variable about 0. Okay, so if A is equal to the expected value of x, now the expected value of x here, as we're going to see later, is actually the mean of x. We've talked about the long-term average, the average of x. If A is equal to the expected value of x, or the mean of the random variable x, we have what is called the central moment, or the moment of the random variable about the mean. Thus, we can compute the raw moment of x, the arrowed raw moment of x, just as we can compute the arrowed non-central moment of x. Okay, so the difference being that when we are computing the arrowed raw moment of x, it is usually about the point 0. When we are computing the arrowed raw moment, the arrowed central moment of x, it is usually about the point where it's usually about the mean, which is in other words, the point at which we are measuring the moment is at the expectation of x. So this is what the definition of moment of random variable entails. Now, if you check here, you'll discover that computing the moment of random variable is actually taking the expectation of a function of random variable. Okay, it's actually like we're taking the expectation of a function of a random variable. Now, let us see how this works for both the discrete and continuous cases. Now, if the random variable x is discrete, of course, it will have a probability mass function, a PMF, f of x. The arrowed moment of x about a point A can be computed using this relation here. You can see what's happening here. We are taking the expectation of the arrowed power of x when x is shifted by this constant A. Now, since it is a discrete, x is a discrete random variable, we are going to sum over all possible values of x and multiply by the probability that x will also assume that value. But observe here that all the values of x will be shifted, okay, by this constant A. And of course, we're going to be taking it to the power r, which is this arrow here signifies, you know, the order of the moment, whether it's the first moment, the second moment, and so on and so forth. So this is how to proceed with the computation of the arrowed moment of a random variable about a point A when x is discrete. So suppose again, that x assume a finite set of countable values, x1, x2 down to xn, the arrowed moment of x about any point A would be computed using this relation. So we have xi here are all the values of x is from x1 to xn. And then we're going to be subtracting every value of x1 minus this constant A, we take it to the power r and multiply by the probability that x assumes, the random variable x assume any of these values. So when we sum, we're going to get this. So this formula here is an expanded form of this formula. So we just take the expectation x1 minus the point A raised to power r times the probability of x1 plus x2 minus the point A raised to power r times the probability of x2 down to xn minus A raised to power r times the probability of xn. So, and where this A is some constant, if A is 0, we're going to have the raw moment. If A is equals to the expected value of x, we're going to have the non-central moment. So, and of course, F here is the probability mass function of the random variable x. So this is how to proceed with the computation of the moment of a random variable when x is discrete, okay? When x is discrete. Okay, let's see when x is continuous. So when x is continuous, we make use of the probability density function, okay? By making use of the probability density function, it means we're going to be involving integral. So we have this formula here to compute the arrowed moment of a continuous random variable about the point A. Now, it means we're going to be integrating over the entire range, or of course, if x is continuous, x takes value in some interval on the real line. So we're going to be integrating over the entire interval where x assume its values, and we just, take the integral of this function where f of x is the probability density function in this case. So for example, if x assume a value in this interval a and b, the arrowed moment of x about a is given by this relation. So we're going to be integrating from the point A to B of x minus a down to r, f of x. So dx, of course, we are integrating with respect to x. So this is how to compute the arrowed moment of a random variable x when x is discrete. So for the case of when x is continuous, we make use of the sum once again. When x is, in the case where x is discrete, we make use of the sum. But the case where x is continuous, we make use of integral, where we integrate over the entire interval. X assumes its values. So this is how to compute the moment of random variables. Now, quickly, let's see some certain breakdown of the moment of random variables. The case where a is equal to 0. If a is equal to 0, it means we're going to be having what is called a raw moment. If a is equal to 0 and we are taking the first moment, by taking the first moment, it means r is equal to 1 now. That will give us the first raw moment. The first raw moment when a about 0 gives us the mean. So this gives us the mathematical expectation of that random variable. It gives us the mean of that random variable. So the mean is essentially the first moment of a random variable about 0 or about the origin. So it is the first raw moment of the random variable. The first raw moment of a random variable is usually the mean, it's a measure of the average of that random variable. While the second raw moment is actually used in the computation of the variance of that random variable. So the second raw moment is when a is equals to 0 and r is equals to 2. And this quantity is used for computing the variance. Okay, now let's see the case where a is equal to the expectation of x. In other words, we're going to be computing the moment of this random variable now about the mean, because the expectation of x is the mean of x. So the second, of course, when we are computing the moment about the mean, we are computing this. We're actually computing central moment, as we have said before. So we're computing the central moment. Now, the second moment, okay, the second moment of a random variable about the mean is actually the variance of that random variable. Okay? The second moment of a random variable about the mean is the variance of that random variable. Okay, so you can see this expectation of x squared is coming from this second raw moment. So this is how you compute your when you expand, for example, you expand what is here, you're going to get a term here, you're going to get this term. Okay, so I mean, you're going to get this term here. That's why we often say that the second raw moment is used for computing variance. But if you just want to do it directly, you compute the moment of the random variable about the mean, where that particular quantity gives you the variance. So the third central moment is a measure of asymmetry or a measure of skewness. Okay, this is how we compute skewness. So you see random variables, for example, if we look at continuous distributions, we'll see that some random variables are symmetric. If this quantity is equal to 0, for example, this quantity is equal to 0, means that distribution is symmetric. Okay, the symmetry of that distribution, it means the distribution is symmetric. For example, the normal distribution has a skewness of 0 because it is symmetric. It is not skewed to the right, it is not skewed to the left. It has just one unique shape. Now, if this quantity, which is the third central moment, if it is a positive value, it means the distribution is skewed to the right. That is, it is no longer symmetric, it is asymmetric. However, the asymmetry is to the right. So if this quantity M3 is M3, that is the third moment about the mean, which is a measure of asymmetry, if it is positive, it's a positive value, it means that distribution is skewed to the right. That is a positive value that's greater than 0 now. That's of course. So if it is positive, it means that distribution is skewed to the right. If this quantity is negative, it means that distribution is also asymmetric, but it is to the left because the quantity, the value, the sign of the value is negative. So if this quantity, the third central moment is negative, it means that distribution is skewed to the left. If it is positive, it is skewed to the right. If it is equal to 0, like in the case of the normal distribution, it is said to be symmetric. So the third central moment is used to measure a symmetry, okay, whether a distribution is symmetric or not. Now, the fourth central moment is actually a measure of tail heaviness. How, whether a distribution has a fat tail or some thin tail, okay? Whether a distribution has fat tails or thin tails. For example, if your skewness, if we can also say this is a measure of kurtosis, okay? This is a measure of kurtosis. If your kurtosis value, or I mean this fourth central moment, if the value is greater than 3, okay? If it is greater than 3, we say it is heavy tail. In other words, the tail of this distribution is heavier than that of the normal distribution, okay? We say it's an heavy tail. If it is less than 3, we say it is a light tail or thin tail, for example, like the uniform distribution and so on. So, but for distributions like this, the fourth central moment generally is used to measure tail heaviness. Okay, when distributions that have heavy tail are usually distributions that contain some form of outliers. Okay, distribution that contains some very few outliers in them. So the fourth central moment is a measure of tail heaviness or a measure of kurtosis of a distribution. The third central moment is a measure of a symmetry, whether a distribution is symmetric or it is not symmetric. And of course, if it is not symmetric, it is either the symmetry is to the right or to the left. While the second central moment is a measure of variability, which is variance. The first moment about the origin is a measure of the mean. That is the mean. It gives us the mean of that probability distribution. Okay, thank you for listening today. We've come to the end of our discussion on the moment and mathematical expectation of random variable. So in our next episode, we are going to be looking at some specific and some very, very special univariate probability distributions. Thank you for listening.